So the recording now should be started, and I want to thank and give welcome to our first talker of this wonderful session, which is Zhiyun Cheng from Beijing Normal University. And today he will talk to us about partial dual genus polynomial and its categorification. Thank you very much.
Thank you, Paulo. So can you hear me?
Yeah, we can hear you very well.
Okay, let me share my screen. So can you see my screen now?
Yes, we can see it.
Okay, thank you. First, I would like to thank the organizers for giving me this opportunity to give a talk here. I'm so glad. And today I will talk about the partial dual genus polynomial and its categorification. Well, so my talk consists of 4 parts. First, I will give a very quick review of the ribbon graphs and the partial duality. And second, I will give a very quick introduction to the partial dual genus polynomial. And this talk contains 2 results. And first, I will discuss the ribbon graphs derived from diagrams, and the second result, just as the title suggests, I will discuss how to categorify the partial dual genus polynomial. So let's begin. But first, I will give a very quick review of ribbon graphs and partial duality. Recall that the classical Euro-Poincare duality, suppose we have a plane graph on 2 spheres, and then we can consider the so-called dual graph. And the construction of the dual graph is quite simple. So for each face, 1, 2, 3, for each face of the graph, we associate a vertex, and there is a 1-to-1 correspondence between the edge sets of the original graph and the dual graph. And of course, for each vertex of the original graph, it corresponds to a new face. So we see that the vertex set, there is a 1-to-1 correspondence between the vertex set of the original graph and the face of the dual graph. So this is a very classical construction, but here we want to ask the following 2 questions. The first one is, how about graphs embedded in some higher genus surface, not necessarily oriented surface? And the second one is, if we regard this kind of duality just as the duality respect to the whole set of edges, how can we define the duality just respect to a subset of the edge set? Okay. First, here I want to tell you some basic notions about ribbon graphs. So, actually, ribbon graph is appears quite often in many topics of mathematics, and also it also sometimes is called fat graphs or cyclic graphs or rotation system and so on. Roughly speaking, a ribbon graph is just it consists of some vertex disks and some edge ribbons. So you need to grow each edge ribbon to some vertex disks. I mean, something like this. So here we have 3 examples. So for the first example, it consists of 2 vertex disks and 3 edges. And for the second one, it also contains 2 vertex disks and 3 edge ribbons. But you can notice that every edge there is half twist here. Well, I would like to remark that all the ribbon graphs considered in my talk are just the abstract graphs. So they are not embedded in the 3 surface. So for example, this one could be overcrossing or undercrossing, so it doesn't matter. It's just abstract graph. Yes. Well, here we have another viewpoint of ribbon graph. We can consider graph embedded in a surface. And if we take a regular neighborhood of it, for example, here we have a torus, and this is a graph, right? And it has 1, 2, 2 vertices and 1, 2, 3 edges. So if we take a regular neighborhood of it, then we will get a ribbon graph, which is just the first ribbon graph. Yeah. So I think in about 2009, Shumtov first introduced the notion of partial dual. And suppose we have a ribbon graph, and we fix a subset A, which is a subset of the set of edges. And then we can define a new ribbon graph, and we use GA to denote it. And how can we construct it? First, we consider the spanning surface FA, and which are just containing all the vertices of G and just the edges in A. So just a subset of edges are grouped to these vertices. So in general, this surface is not connected. And then for each boundary of this surface, we introduce a vertex of a new ribbon graph. And there is a one-to-one correspondence between the edge set. But for each edge not in A, it still lives in a new ribbon graph. But for each edge belongs to A, it corresponds to a new edge in a new ribbon graph. So we know that now the new ribbon graph, the number of the vertices is just equal to the number of the faces of A. Here we just simply use the capital letter A to denote the ribbon graph consisting of all the vertices of G and just the edges in A. And of course, the number of the edges are equivalent. So here is an example. Here we have 2 examples here. So for our first example, here we have a ribbon graph, and it consists of 2 vertices and 3 edges. Okay, and we just call them 1, 2, 3, and we choose the subset to be the third one, the third edge. Yes. So the first we can consider the surface FA. FA means that we just remove all the edges not in A. So we have a surface FA, and we should recall the place where sorry. We should recall the place where the first edge and the second edge, glued to these 2 disks. So we have 1, 1 here and 2, 2 here. But for the third one, we should use these 2 arrows to denote where the new edge are glued. So here we have 3 boundaries. So it corresponds to 3 vertices of the new ribbon graph. And then we just glue and here and 1 here and 1 here. So we will have a new ribbon graph, which is just the partial dual graph of the G1 with respect to this subset. And similarly, we can also consider the subset which contains 2 and 3. And again, we just remove the first one, and we recall all places where the edges are grouped, and then we have two vertices, and we glue the edges back. We will have some new ribbon graph like this. Well, there is another way to construct the partial dual. So if we take a subset of the edges, we can take the partial dual once just for a single edge. If this edge connects two vertices just like this, then we just emerge these two vertices into one, and the new edge is grouped in this way. And if the edge E connects a vertex to itself, so we have two cases. The first one is the vertex and this edge is orientable, just like this. And we just split these vertices into two vertices, and the new edge is grouped like this. However, if the vertex together with this edge is non-orientable, we just define the partial dual with respect to this edge like this. You should notice that we take a notation about this part, in this way. So here we have some very basic properties about the partial dual. The first one is the partial dual is orientable if and only if the original ribbon graph is orientable. And the partial dual is connected if and only if the original ribbon graph is connected. And in particular, if we choose the subset to be the whole set of the set of edges, so we just choose A to be the EG, and now we can recover the classical Euler-Poincare duality. Yeah, the classical dual. And if we choose two subsets A and B, we found that we can take the partial dual for A first and next for B, and we see that there is some communication here, and the result is nothing but just to take all the vertices in this set. And of course, so the fifth and the sixth properties are just the corollaries of the first one. And if we take the partial dual for with respect to A twice, then we will get the original ribbon graph. Okay. So now let me tell you what is the partial dual genus polynomial. I guess it's a polynomial in one variable and with a long name. Yeah. So for a ribbon graph, let us use epsilon g to denote the Euler genus of this ribbon graph. And this is the definition, but I just want to tell you that this is nothing but if the embedded surface, the embedded surface means that if we have a ribbon graph and if we glue we glue one disk along each boundary, then we will have closed surface, and we call it the embedded surface. If it is orientable, then epsilon is just twice the genus. And if it is non-orientable, this is just the cross cap number. I mean, if you consider the Kern sum of some projective plane, and this is the number of the RP2. Yeah. Okay. So about 5 years ago, Gross, Mansur, and Tucker, they introduced the so-called partial dual genus polynomial. And it's a polynomial in variable z, and you can find that it's a sum, and the sum takes over all the subset of the set of edges. And we just put the Euler genus here. So it's easy to see that this is polynomial in Z, and of course all the coefficients are non-negative. And here are some very basic properties. First, you should find that if we take the Z to be 1, and then, of course, this is equal to 2 to the power of the number of edges. And in the same paper, they show that we know that in graph theory, people are very interested in some properties about the polynomial. For example, we know that Junha, his famous results that the collimatic polynomial is low concave. But for this one, in this paper, they find some ribbon graph, and this polynomial is not log concave. Yeah, seeing the same that is not so good, but it behaves quite well under some local operations for ribbon graphs. For example, if we take the disjoint union or the ribbon join, so this is the definition of the ribbon join. So the partial dual genus just take the product of the two polynomials. And if we take the bar amalgamation, so the bar amalgamation means we add an edge between two ribbon graphs. So this is graph 1, this is graph 2, and then we add an edge here. So the result is just twice the product of the partial dual genus polynomial of the two ribbon graphs. Okay. Our first very simple result is we can rewrite this the definition of this polynomial, and of course you can see that for a fixed ribbon graph, this part is just a constant, and so we just want to know how to calculate the this part and this part. So FA means that it's just the number of boundaries for a ribbon graph A. A means the ribbon graph which consists of all the vertices of the original ribbon graph and just the edges in the subset A. And similarly, you can define the complement of A. So here is an example. This is a very simple ribbon graph. I put a half twist here, but you can see that this is just one disk, and we have two edges here, 1 and 2. So by using this result, if we want to calculate the partial dual genus, then we can consider all the subsets of the set of edges. It means empty set, 1, 2, and the whole set. So in this way, we can calculate that the partial dual genus polynomial of this ribbon graph is just 2z squared plus 2z. Yeah. So is there any question right now? Okay, let's just continue. In my talk, I will mention two results. The first one, we will consider the ribbon graphs derived from chord diagrams. So first, I will tell you what is a chord diagram. So roughly speaking, a chord diagram is just an oriented circle with some chords inside. Here, I will show you some examples here. So for this chord diagram, it has just one chord, and this 2 has 2 chords inside, and this 5 chord diagram have 3 chords. Of course, 2 chord diagram are considered to be the same if they if one can be by taking some homomorphism into another one. So how to construct a ribbon graph from a chord diagram? Actually, it's quite simple. So if we have a chord diagram like this, So first, we can imagine that this circle bounds a disk, and then each edge will correspond to edge ribbon, just like this, 1 and 2 and 3. As I mentioned before, here all the ribbon graphs are just abstract graphs. So the over-under crossing here is not important. So we can draw it in this way. So for each color diagram, we can define a ribbon graph. Of course, not every ribbon graph can be obtained in this way because, of course, here we just have one vertex here, one vertex, yes. Why we are interested in this kind of ribbon graphs is because about 2 years ago, Chumtov, he found that if we consider the partial dual Genus polynomial as a function on chord diagrams, then it satisfies the following four-term relation. I think people who is familiar with the finite type invariant theory will be must be quite familiar with this four-term relation, and it plays a very important role in the finite type invariant theory, or also called it Konchevich invariance, or I'm sorry, Vassiliev invariance. In the end of Chumtov's paper, he asked some questions. The first one is, I think in 1995, we know that there does exist some finite type invariant not come from the algebras, but however, this is not a constructive invariant. So all known constructive example of real systems all come from the algebras. So he wants to know, does partial dual Genus polynomial with the system come from some Lie algebra? But in my talk, we will just focus on the second question. Chumtov asked the following question. We know that a chord diagram determines an intersection graph. So I will tell you what is the intersection graph. So for each chord, it corresponds to an edge. And if two chords have an intersection point, then we add an edge between the two vertices. So you see that 1 and 3 have a intersection here. So we add an edge between them. So similarly, we add an edge between 3 and 2. But since 1 and 2 has no intersection point, so 1 and 2, there is no edge connecting them. So of course, different chord diagrams may correspond to the same intersection graph. But by using a result of Shen Anjing and his student Yan, we know that the partial dual Genus polynomial depends only on the intersection graph. So Chumtov asked that, can a partial dual Genus polynomial just be defined in terms of the intersection graph? And can we extend its definition to all graphs? I mean, not just the intersection graph from some chord diagrams. And finally, the most important point is he wants to know, does it satisfy the four-term relation on graph defined by Landau about 20 years ago? I will give an answer to the second question. So first, recall that the definition of the partial dual Genus polynomial. This is the definition, and we know that this part is just a constant. So we just want to read this part from the intersection graph. Yeah, we just want to calculate FA and FAC from the intersection graph. Actually, for each graph, there is an adjacency matrix. So, for example, if we have a graph which consists of 4, 1, 2, 3, 4 vertices, then the corresponding adjacency matrix is a 4 by 4 matrix. And if two vertices are connected by an edge, then we write 1 here. And if two vertices there is no edge between them, so we will write 0 here. So this is the adjacency matrix. And the result of Landau, he proved that, I'm not sure whether this result was first proved by him, maybe much more earlier. Some people find the same result, but I know this result from one of his paper. And Landau's result is that for intersection graph from a Rubin graph, the number of boundary components is equal to the co-rank of this matrix plus 1. So I will explain this result by using this example. Here we have a chord diagram. It has 4 chords. So we can see that the corresponding Rubin graph have 3 boundary components. Right. The first one, and this is this is the second one. This is the third one, and the corresponding intersection graph is nothing but this one. Yeah, it's the same one, and we can calculate the co-rank of it. It's just 2, and we have 2 plus 1 is equal to 3. That's 3 here. Okay, so by using this result, we can answer the second question asked by Chumtov. And actually, we show that we can just calculate the partial dual Genus polynomial by using the rank of 2 matrices. And these 2 matrices are just can be defined from the intersection graph of the corresponding graph. Yes, and if we have a graph which is just maybe not came from like maybe it is not an intersection graph from some chord diagram, we can also define a polynomial in this way. Yeah, because any graph we can define the adjacency matrix, and then we can define what is MA and what is MAC, and then we can have a polynomial like this. And our main result is if we use this definition, the partial dual genus polynomial, it does satisfy the 4-term relation introduced by Landau, and it satisfy this 4-term relation. Here, lambda is just a graph, and AB are 2 vertices, and lambda AB prime and lambda AB tilde are 2 new graphs constructed from the original graph lambda. So here's the definition of lambda prime, and here's the definition of lambda tilde. But I don't want to go to detail of the definition here, but I just want to tell you that this 4-term relation has some very close relation related to the 4-term relation in finite type invariant. Yeah. Okay, here we have 2 remarks. First, I want to remark that actually this result was also obtained by Deng, who is also an organizer of this wonderful conference, and Dong and Professor Shen Anjun and Yan in the same time. And I guess Professor Jing will give a talk in this conference, and he will discuss something closely related to this result. Yeah, and actually, I should tell you that they find some more powerful result about this theorem. Yeah, they extended it to some more general objects. Yes, and for the first question, recall that the first question is. Does the partial dual genus polynomial with the system come from some algebra? almost at the same time, it was pointed out by Meta that the partial dual genus polynomial weight system actually it comes just from the Lie algebra GLM. Yeah, not something new. It also came from some Lie algebra. Okay. So is everything good? Okay. So next I will go to the last part of my talk, and just as the title suggests, I will discuss the categorification of the partial dual genus polynomial. So roughly speaking, just as the first talk given by Professor Kornoff, here by categorification, I mean that I will introduce a homology theory such that the graded Euler characteristic is equal to the partial dual genus polynomial. But I have to say I cheat you in the title because I will not categorify the partial dual genus polynomial. Actually, I will categorify the graded partial dual genus polynomial. So first, I will tell you what is the graded partial dual genus polynomial. So the graded partial dual genus polynomial can be regarded as a refined version of the partial dual genus polynomial. So this is the definition. For a Riemann graph, we can introduce a two variable polynomial in this way. So we add a new variable w here. And also the sum is taken for all the subsets of the set of edges. And here we just add a one term like this here. So here this means the number of edges in the subset A. And it is very easy to find that if we take the omega to, if we take the W to be 1, then we will recover the original partial dual genus polynomial. And it is very interesting to point out that if we write the graded partial dual genus polynomial in this form, I mean, just like in the form of W, and we can regard the coefficient as a polynomial in Z. There is some symmetry about the coefficient. Fi is equal to Fn minus I here. Yeah. So now we introduced another polynomial which has two variables, W and Z, and we know that it can be used to recover the original partial dual genus polynomial. So what we want to do is to introduce a homology theory, actually more it's a core homology theory, and the graded partial dual, the graded Euler characteristic is equal to, maybe I should say, can be used to recover this graded partial dual genus polynomial. Okay. Next, I will show you what we want to do. So this is just the same example, and I show you how to calculate this graded partial dual genus polynomial. And the result is here. And if we take the W to be 1, then we will get the original partial dual genus polynomial. Okay. Here's the main idea of the categorification. First, we need to choose a commutative Frobenius algebra. Here we choose R to be the minimal ring contains all the integers and root 3, and we use M to denote the R module. We equip the operation unit U, which just sends 1 to 1, and the multiplication is just the natural one. And we define the Frobenius trace from M to R, which sends 1 x to 0, and which sends x squared to 1. Also, here we have a core multiplication, and from M to M tensor M. So here is the definition. So the most important thing here is we need a so-called half genus map. It's a map from M to M, and it sends 1 to root 3x, and it sends x to 3x squared, and it sends x squared to 0. So you can see that this map just take the multiplication by root 3x. Yeah. And we set the degree of 1 to be 1. We set the degree of x to be 0, and we set the degree of x squared to be minus 1. So this setting will make the multiplication, the half genus map, and the core multiplication, they will have degree minus 1. We know that there is a one-to-one correspondence between commutative for this algebra and the two-dimensional TQFT. And for this case, it also has some topological interpretation. So here we have a so-called punctured 1+1 dimensional TQFT. And so this is the if we use this direction, so this is the birth, this is the death, and here is the half genus map H, and we use a puncture here to denote it. And this one is the multiplication, and this one is the core multiplication. So this is from M times M to M, and this one sends M to M times M. So why we call this map the half genus map? This is because if we consider the M square, and it is equal to the composition of first we take a core multiplication, and then we take a multiplication. So M square is equal to M composite the core multiplication. And you can see that this puncture can be moved on the surface smoothly. So this result guarantees that we, from the topological viewpoint, we have some equation like this. Okay. Here I just want to remark that actually this kind of TQFT is just a special case of the so-called long-oriented TQFT introduced by Turef and Turner about 10 years ago. Yeah. So by using this, we can construct 4 n cubes. And later I will use the tensor product of these 4 n cubes to define the quotient complex. So I don't want to go to the details of these definitions, but I just want to tell you the effect of them. So the first one, the first n cube is used to make the tensor product of the 4 cubes to be anti-commutative, because this one is an anti-commutative n cube, and the 3 other n cubes are all commutative. So if you take the tensor product of them, you will get an anti-commutative n cube. And the second n cube is used to balance the, because if we take the graded Euler characteristic, we have some oscillating sum there. So this one is used to balance that sign. And here we introduce another variable y, and the degree of y is 1. So we have two things here. The first one is x, and the second one is y. And the third and the fourth cube are used to categorify the FA and FAC. So here we use the product, the core product, and also the half genus map. This is one why we need the half genus map here, is because if we add an edge to a disk, it is possible that the boundary, the number of boundaries are the same. So we just for this case we will need this kind of half-genus map. Okay, so roughly speaking, we just take the tensor product of all these 4 n cubes, and then we can define the quantum dimension of M in this way. So we have 2 variables here. Here's M and N, and it came from the degree of X and Y. Yeah. And now,
sorry to interrupt. 5 minutes left. Thank you very much.
Okay. So now, so in this way, we can define a partial dual quotient complex, and in this way, and here we need to shift the degree, just like the in the homology. Now also need to shift the degree to make the differential preserve the degree. Yeah. Okay, so the main result of the first part is for any ribbon graph, and this quotient complex is well defined. I mean, all the definition, I mean, you need to fix something, for example, the order of the edges and all these things, and will not, will just give you the same quotient complex. And I'm sorry, the quotient curve may be not the same, but the cohomology groups is well defined. And the graded Euler characteristic is equal to the graded partial dual genus polynomial up to multiplication by some constant. Of course, you need to write W in this form and Z in this form. Here is one example. So for this example, we have calculated the partial dual genus polynomial and also the graded partial dual genus polynomial. So for this, we can find that the Poincare polynomial of the homology just something like this. A little complicated, but if we take P in this form and J inverse to be Q plus 1 plus Q inverse, and we will find that the Euler characteristic is equal to this one. And this is nothing but if we do not consider the fixed term, and these two parts are equivalent. Yeah. Okay. So we have some final remarks here. First, I want to mention that the cohomology may contain some torsions, and these torsions cannot be read from the polynomials. And we do find some ribbon graphs which have the same polynomial but different cohomologies. And finally, some equations, as I mentioned before, we have some equations here, and these equations can be categorized into just long exact sequences. Okay. Yeah, this is a picture taken by myself about 8 years ago, and I really appreciate many important contributions made by Louis to not just the knot theory, but also to the community of the knot theory. And happy birthday to Lou. I think I should stop here. Thank you.
Thank you very much for the wonderful talk. And now I will stop the recording.